So our next speaker is Tomas Jochym-O'Connor. I've forgotten, where are you based now? It doesn't say on your first slide.
I am in IBM.
IBM.
Yeah, so thanks Earl. I'd like to thank all the organizers, Earl, Barbara, and Steve, for initially putting together this workshop, and then when the pandemic hit, to rearrange it for this online webinar. I think that's great, and for all the non-local organizers for helping put together this Slack channel and everything. I know it's not ideal, we're not in the Spanish mountains, but at least we can talk about quantum error correction and have these channels to discuss ideas. So along those lines, I would like, if you have any questions, just of course during the talk, write them in the chat. But after the talk, you can write them in Slack or email me if you prefer. My email's at the top right. So yeah, this is work that I have done with Ted Yoder at IBM, and it's about 4D toric codes and how to get logical non-Clifford gates in 4D toric codes. And this work should be appearing shortly on the archive. Okay, so here's a little roadmap of what I'll be discussing today. I'm going to talk about, generally speaking, I'm going to review topological codes in D dimensions and what are their restrictions. And then I'm going to go over for our requirements for multi-control logical Z gates, in the context of CSS codes. So in this talk, I'll be talking only about CSS codes. And then I'll have a little aside and talk about honeycombs and their structures and how we can label them, because this will be very useful in our search for a lattice that will allow us to do a logical cccz gate in 4D. And then I'll discuss a little of some of the properties of this code that we found, stabilizer weights, discuss a little bit about the existence of meta checks, etc. Okay, so I mean, really, this work builds upon a great foundation of past works, which a subset of these I've listed kind of at the bottom, and I'll flash a reference slide at the very end. But really, it builds upon the previous works that have been going on in the community in the last, let's say, 10 years. And it starts the kind of, one of the fundamental works is this result by Bravi and Koenig, which shows this connection between the gates, the transversal logical gates you can obtain for a topological code in a given spatial dimension. And, from a high level, what they show is that if you have a 2D topological code, you can do Clifford gates, transversal Clifford gates. If you have a 3D topological code, you can do transversal third level gates that are at the third level of the Clifford hierarchy. So that's like T, CCZ. If you have a 4D code, you could do square root of T, cccz, which are the fourth level of the Clifford hierarchy, etc. And so this is really nice. It kind of puts the framework on what is allowable in a given dimension size. And so it kind of shows you what you should be looking for. And along these lines, I mean, kind of in parallel, Hector Bombin showed that in his color code constructions, showed that the color code family saturated these bounds, and namely in 3D gave you a transversal T, and then more recently in the past few years, like Vasmer and Dan Brown showed that for a particular construction of the toric code in 3D, you can get a transversal CCZ. Okay, and so what I really want to frame this work that I'll be talking about as sort of the generalization of this Vasmer-Browne idea to 4 dimensions. Okay, so in 4D, what's previously known is, like I said, the color codes provide you a transversal square root of T or pi by 16 gate. but there are no known constructions for like a native cccz gate. Now, of course, you could get this by combining the square root of t with other Clifford operations because it's universal and get your cccz this way. But we were looking for something that was more native. And this is kind of in contrast. So generally speaking, there's a very famous 4D toric code that from the early 2000s that was introduced for the purposes of self-correction. And in that model, you actually get a transversal Hadamard. And the reason for that is the logical X and logical Z mirror each other in terms of their dimension size. So in order for it to be self-correcting, one of the requirements is that the logical operators are membrane-like. So they're both going to be two-dimensional planes. And so they're kind of on equal footing, X and Z. But if you want to get a gate that's in a higher level of the Clifford hierarchy, you actually need an asymmetry in the logical operators. And this was kind of follows up from work on disjointness that I've done in the past few years with Alex Kupsa and Ted Yoder. And so what we're going to be looking for is a 4D code where one of the logical operators is three-dimensional and the other logical operator is one-dimensional on a string. Okay, and so that's kind of the framework behind what we're going to be looking at. And so this is not it's going to turn out to not be just a straightforward generalization of the hypercubic lattice, which is what we kind of expected when we first went down this path. Okay, so that's kind of setting the previous works and motivating what we're going to be looking for. So I want to talk a bit about, like I said earlier, I'm going to be focusing on CSS codes, and I wanted to discuss what are the requirements for a CSS code to have these logical multi-controlled Z gates. And I'll start with just a logical controlled Z. And just for notation purposes, first let's look at this top this circuit here that I have on the slide. What it says is that under the action of a controlled Z gate, the X operator, an X operator on a given qubit will get mapped to XZ, where it propagates the Z onto the second qubit. Okay, and of course, because controlled Z is diagonal, it's going to preserve all poly Z operators. We'll leave them unchanged. And so if we're looking at, we would like to have a logical controlled Z gate. So a transversal logical controlled Z gate, what we would like is that the stabilizers of the original code to be preserved. That's the kind of definition of a logical gate in stabilizer codes. So if I use this script notation here to define the stabilizers, so the script Xi is the ith X stabilizer on code block A. And if I have a bar over top, that's going to be the ith logical operator on code block A. And what the overlap conditions are is that, so under the action of a transversal CZ, you're going to map your X stabilizer to a Z operator on the same qubits, but on the second code block. And what you'd like is those Z stabilizers to commute with the original stabilizers of the code. So you'd like them to have even overlap with the X stabilizers from the second code block. So that's this first constraint here, is that if you look at a given qubit support, the X stabilizers from code block A and the X stabilizers for code block B intersect an even number of times. And so their overlap is 0, not 2. And similarly, you don't want to map the X stabilizers onto a Z operator that anti-commutes with the logical operators themselves. So you also want that this intersection to be 0 between an X stabilizer and an X logical operator on the second code block. So that's the second condition. And in order for it to actually implement a logical controlled Z across multiple encoded qubits, you want that the logical operators don't intersect unless they're conjugate pairs. So the ith logical operator, X operator, only intersects with the jth logical operator in the second code block an even number of times unless they're conjugate pairs, so that their label is the same. Okay, so that's the high level what you need for a logical controlled Z. And now we can generalize this to what do you need for a logical controlled Z. And the key for understanding this is under the action of controlled Z, an X operator gets mapped to X and controlled Z on the other two blocks. Okay? And so you can generalize these overlap conditions requirements. And basically what these first three requirements are saying is kind of like a generalization of what I had on the previous slide, but saying that if you look at the action of controlled Z on an X stabilizer from one code block, that's going to get mapped onto a controlled Z on the other code blocks. And now you want that controlled Z on the other code blocks to actually be the logical identity, because you want this X stabilizer to be mapped to something that's in the stabilizer group. And so that's just regeneralizing the conditions from the previous slide for the action when you're restricted to just the X stabilizer from code block A to be logical identity. So that's why you have this 0 in the third line. And the last line is just a condition that you're actually going to be implementing logical controlled Z, and so that the overlap of the X logical operators from the 3 code blocks is only odd if you have the same labeling for I, J, and K. Okay? And so unsurprisingly, you can generalize this even one step further if you're looking for controlled Z. And there's a similar very nice relationship, is that X now under the action of this multi-controlled Z gets mapped to X on the first code block and the controlled Z on the other 3 code blocks. And so it's pretty straightforward to just generalize these conditions. You're just kind of adding one extra code block. I won't go through all the steps, but kind of the important criteria that I'm really going to be focusing on this talk, and this is kind of in the last 3 slides, the one thing you have to remember is that if you look at the X stabilizers if you want to have a logical controlled Z that's transversal among 4 code blocks, the key requirement is that the X stabilizers for the 4 code blocks, they overlap among themselves. When you look at their overlap across the 4 code blocks, is even is even. Okay, so this is really the condition that I'm going to be focusing on. The other conditions are equally as important, but this is kind of the one I'll be focusing on, and the other ones will kind of fall out once we find a lattice or an appropriate lattice. So I won't really focus on the other ones as much. Okay, so that's kind of an aside on the requirements and what we're going to be looking for in this talk. Okay, so you might ask, a natural question is, why do we even care about cccz? You know, controlled Z is in the 3rd level of the Clifford hierarchy. So if you combine that with Clifford gates, that's enough for universal computation. So just like in the previous talk, you know, we're looking for schemes for universal computation on logical qubits. And the idea here is this is a method that's could be potentially alternative to magic state distillation, or it could even be used in a magic state distillation scheme. But it's really kind of a separate avenue in terms of looking for universal applications. And so if CCZ was enough, then why are we even concerned about these cccz gates? And one motivation that's kind of nice that we've come to realize, and kind of a nice observation, is pretty obvious when you think about it, but is that if you have suppose you have some logical action that where cccz transversal across all the qubits in your code implements a logical cccz gate on multiple encoded qubits. So in this scenario here, I'm looking at, we have 2 encoded logical qubits per code block, but you know, you could have K could be arbitrary. And it's kind of natural that this operation will actually end up implementing cccz across all of the K logical qubits. We can actually use this gate to then obtain a targeted logical CCZ, because it might be that you don't actually want to implement CC, you know, either CCZ or cccz across all the logical qubits. You might actually only want to do it on one particular set of logical qubits. And this is what I call the Pauli sandwich trick. is that you can take, you can implement cccz transversally, then implement a logical X on one code block, and then do cccz again. If you look at its logical action, you get these multi-controlled Z gates sandwiched by a logical X. But I said in the previous slide that logical X under conjugation gets mapped to CCZ on the other code blocks. And then the CCCZ gates will actually cancel each other out, right? And so you end up getting a targeted CCZ on one of your code block, on one logical qubit in your code blocks, and the other three blocks. And then you can, and since X is transversal, you know, any poly operator is transversal in a stabilizer code, this global operation is going to be transversal as well. Okay, so this is kind of one motivation, is that, you know, if you had codes that implement this logical CCCZ gate on multiple encoded qubits by doing a transversal operation, then this allows you to get a targeted CCZ gate on a subset of code blocks. Okay. So now I'm going to kind of shift gears completely, and I'm going to talk a bit about the structure of lattices and these Schlafli symbols. And this is kind of help us in our search for a code that has the properties we're after. Okay, so I'm just going to build this up from the ground up here. So what is the Schlafli symbol? So if you have a one-index Schlafli symbol, that just represents an n-sided regular polygon. So Schlafli symbol of 3 is just a triangle, 4, square, 6, hexagon, right? Very straightforward. So now you can generalize that. If you have two labels, then this will represent, it represents an NM Schlafli symbol is a polytope with m n-sided polygons around each vertex. So you kind of read this from right to left. So a 3-3 has 3 triangles around each vertex. So that's just a tetrahedron, right? As if you look at each vertex, it has 3 triangles around each vertex. And so a 3-4 has 4 triangles around each vertex. And that's just going to be your octahedron, right? If you look at a given vertex, you have 4 triangles around each vertex. And a 4-3 has 3 squares around each vertex. That's a cube. And something that's really nice, a nice feature of these Schlafli symbols is that you can kind of derive the dual of a given object by just reversing the order of the labeling of the Schlafli symbol. So octahedron is dual to the cube and vice versa, while the tetrahedron is self-dual. Okay, so this is going to be something that we're going to use later in the talk, and this is true generally. Okay, but if you have 2 labels, it can also represent a honeycomb, a 2D honeycomb, because a 4-4 also has 4 squares around each vertex, and so this is just a square lattice. It's a 4-4, and a 6-3 has 3 hexagons around each vertex, right? So it's kind of confusing, but a Schlafli symbol with two labels can either represent a 3-dimensional polytope or kind of a 2D honeycomb. And this just has to do with internal angles. You can kind of think of them as one, but just you've opened up the internal angle. Okay. Okay, and then we can take one level, again, taking one more level of abstraction, you can take a Schlafli symbol of 3 labels. Again, reading from right to left, this is either a 4D polytope or a 3D honeycomb that has P, so reading right to left, P objects NM around each edge. So we increase the dimension size around each so instead of around a vertex, we're looking at around an edge now. So maybe I'll focus on the right one first. The cubic honeycomb is a 4-3-4 because around each edge we have 4 4-3s, and remember a 4-3 is a cube. So around each edge we have 4 cubes, right? You can just look at any edge that has 4 cubes surrounding it. Well, a 433 is a hypercube, so a 4T hypercube, because around each edge you have 3 cubes. So if you look at, say, like this edge here, has the top cube, this middle cube, and the front cube around this edge, right? Okay. And so, yeah, so this is the, and you can, you know, it's unsurprisingly, we can, you know, you can keep increasing the number of labels for these Schlafli simples, and you're going to get, you know, kind of higher and higher dimensional objects. Okay, so we actually had an introduction to this in the first talk of the toric code, but revisiting this, I'm going to do something kind of controversial. I'm going to reverse the labeling, and I'm going to label X stabilizers with plaquettes and Z stabilizers with stars. I know that will be an unpopular choice given the
Thomas,
attendees.
can I just interrupt and ask a question about the previous slide? Sorry, it was just one thing that I didn't quite get. So you said the honeycomb lattice. Sorry, I normally think of the honeycomb as being like hexagonal tiling or something. So what do you mean by honeycomb?
Oh, sorry, I'm just using the general term of like a lattice, like a regular lattice as a honeycomb.
Honeycomb in your language just means regular lattice.
Yes, regular. Sorry. Yes. Not necessarily this 6-3 that I think you're referring to. Yeah,
okay. And Andrew Landell's got a question as well.
Sure.
And maybe you're going to answer this later on because you haven't given us the constructions yet. So he's asking about how there's the smallest interesting color code has a logical CCZ gate, which has transversal single qubit implementation by T gates. And are there examples of 4D surface codes or color codes that have a single qubit implementation at cccz?
Maybe we could revisit that at the end of the talk.
Okay.
I'm going to assume I probably might not have a direct answer to his question, but maybe it will become a little bit clearer as we go along.
Okay.
Yeah, no problem. Okay. Okay, so why am I kind of taking this controversial view? I mean, it's really more I want to have in the dual lattice, the dual lattice of the square lattice is actually the square lattice itself. But in the dual lattice, the X stabilizers are going to be given by vertex operators. So the dual lattice is going to be what is the lattice you all think of traditionally in the toric. Okay, it's just for convention purposes. But all right, so maybe let's get into the interesting stuff. So let's look at the 3D toric code. So we have the 3D cubic honeycomb or the 3D cubic lattice. The qubits here are these white circles. They live on edges. The vertices, which are at the corners of these cubes, are where the X stabilizers live, and the Z stabilizers live on faces. Okay, so if this is the exact same lattice, I've just kind of added a few extra qubits and shown explicitly these X stabilizers are these yellow 6-body operators, right? So if you look at, it's kind of, because they're kind of cut off here, but if you look at the internal one, you have the top, bottom, left, right, and front, back, right? So these are the X stabilizers, and the Z stabilizers are these 4-body faces of the cubes, and it's fairly clear to see that they commute because any face intersects at most twice, or at exactly twice with any adjacent vertex operator. Okay, and the Z logical operator is going to be a string that's going to move along the Cartesian coordinates. And here they're actually, if I look at a periodic lattice in 3D, there are going to be 3 logical operators because there'll be an X string for each of the Cartesian directions, and the corresponding Z logical operator will be a membrane that's parallel, that's orthogonal to that string. Okay. And now I would like to discuss this nice result from Vasmer and Browne, where there's a typo here on the slide. This should be the model for controlled Z on the 3D toric code. And the idea there is, so you want to find an encoding of 3 code blocks on this square lattice that allows for the implementation of controlled Z. And what's interesting about this model is that there's an asymmetry in the code blocks here. And how they define their code blocks are, you take the same lattice, the cubic lattice with qubits on edges, and this is still the cubic lattice. I've just kind of cut out the corners of the lattice. And so here are the X stabilizers we were talking about last time. So the X stabilizers for one of the code blocks will remain the same. But now if I look at the X stabilizers for the other two code blocks, we're gonna alternate the cubes of your lattice, the coloring in red and blue. And the X stabilizers for one code are gonna be the red. The red cubes are, but actually if you look at these objects, they're cube octahedra. And the blue stabilizer, or the second code block is gonna be the blue stabilizers. Okay, and so these are weight 12 stabilizers. And the Z stabilizers of a given code block will be given by the intersection of X stabilizers from the other two code blocks. Okay, so if I look at the red code block, these are the X stabilizers are these red cube octahedra. And if you look at the intersection of a yellow Z stabilizer and a blue Z stabilizer, that gives these weight 3 faces. And each of these weight 3 faces intersects an even number of times with the X stabilizers. So another way of saying this is that this satisfies the overlap conditions I was talking about at the beginning, where the X stabilizers for the 3 different code blocks intersect an even number of times, right? And so you naturally define the Z stabilizers based off the intersection of 2 of the code blocks. And so this will allow you to get a transversal CCZ gain. Okay, and so the way we like to think about it in our language is look at the dual lattice. And the dual lattice of the cubic lattice is the cubic lattice itself. And now the 2 red and blue code blocks, the stabilizers, instead of them being volume-like, are now going to be represented by vertices. And that's going to be these red and blue vertices. And we're going to alternate. So we're going to 2-color the vertices so that no vertices of the same colors never share an edge. They only ever share a face. And the qubits now live on the faces instead of the edges, because we're the dual lattice. And that's, so the faces are D-1 cells in this object. And the overlap condition amounts to, is that any edge is adjacent to 4 cubes, with each of which it shares at most 2 faces. And so that's the overlap condition, because if you look at the intersection, so the traditional X code, that's going to be represented by the cubes now, the 3 cells. And if you look at the intersection of a given cube with an edge, it intersects at most at 2 faces, or exactly 2 faces. And those 2 faces guarantee you an even overlap condition. Okay, so we're going to be thinking now, we're going to take this Vasmer-Browne construction, and we're going to be looking at X stabilizers given by vertices and qubits placed on D-1 cells when we go to 4D. Okay, and just a quick aside in terms of this condition, so that you're actually getting a logical CCZ gate, you need that the membranes of the given logical pair intersect. So if you look at these 2 membranes for X, remember the X logical operators were membranes, they intersect along a line, and that line is exactly the Z logical operator for the 3rd code. Okay. Okay, so here is the requirements that we're going to be after. So in general, what are we looking for? Qubits are placed on edges in the primal lattice. In the traditional sense, qubits are placed on edges. We want this restriction that we have string logical Z operators, because we want the Z logical operators to be 1-dimensional. So a Z error gives rise to a pair of syndrome violations. I want this to hold for all code blocks. So our requirements in D dimension is actually we're now going to look at the dual lattice. So instead of qubits being placed on edges, they're going to be on D-1 cells. That's the dual component to edges. The vertices of the dual lattice are going to be D-1 colorable, such that any 2 vertices of the same color share at most a D-1 cell. So what's that saying is that if you have 2 vertices of the same color, they share at most a qubit. And so any qubit is going to give rise to a pair of pairs, or sorry, of syndromes. Yeah, and that's each d-1 cell has two vertices of each of the d-1 colors. Okay, so kind of what we're talking about in 4D is when we're looking in this dual lattice, we want the qubits to be on 3 cells, so to be in volumes. And we want those 3 cells to have vertices that are 3 colorable, such that no vertices share an edge or face of the same color, share an edge or face. And the natural candidate there is the octahedron, right? The volume, you have the qubit will be represented by an octahedron, and the stabilizers will be these vertice operators, and such that no vertex of the same color shares an edge, right? And so you can 3 color. So the octahedron is given by Schlafli symbol 3,4, like I discussed earlier. And so what we're going to be after is finding a honeycomb whose Schlafli symbol is 3,4 AB. Okay, so AB is our degrees of freedom here, but we want this 3,4 because basically what that's saying is that it's made up of these octahedra, which we can hopefully 3 color. And our candidate honeycomb is going to be this octuplex honeycomb, which is...
Can I just ask a question on the slides? You're saying
Sure.
that you want a 3 cell whose vertices are 3 colorable. So anything that's 3 colorable is also going to... would something that is 2 colorable also work, or...?
No, we want 3 colorable because we're going to define 3 of the code blocks by these 3 colors. And then the 4th code block is going to be actually kind of represented by the 4 cells. So an analogy
like
to
anything that is 2 colorable is 3 colorable in a sense. There's like an extra assumption is there in the sense that you want some symmetry between the colors? If you say something is K colorable, you usually mean that it can be colored with K colors or less.
Yeah, I guess, well, we also want that every qubit is going to be giving rise to, you have like a Z error gives rise to a pair of excitations or a pair of syndrome violations in the 4 code blocks. So that's why I think we have the 3 of the colors here are going to be paired to a single qubit in for this octahedron, and the 4th one will come from these 4 cells.
Okay.
I don't know if that makes it clear. Maybe we can address this afterwards. So that's this 3,4 is kind of the basic object that we would like, and the candidate honeycomb will be this octuplex honeycomb, which is made of its unit cell, or it's the octuplex, which is this object 343. And so this is the adjacency graph of the 343. And I mean, you can verify that it's 3 colorable, but this doesn't really give you, this is a 4-dimensional object, just drawn out on the plane. It doesn't give you really much intuition about what's going on here. And so to kind of understand the octuplex, you can construct it from a hypercube. So you start with the hypercube, and you're going to actually place vertices on the faces, and you're going to 3 color these vertices. So if I look at these will be the red faces, so they're kind of the top and bottom of this middle cube, and the top and bottom here, and then this kind of diagonal leaflets coming out. And so no 2 red faces, they never share an edge, right? They only ever share a vertex or a volume. So that'll be your red faces. You can do similarly for the blue, it's like left, right. And then the green faces, front, back. I've omitted the very front, very back here. And then so if you just place vertices there, it gives you kind of this type of structure. This is a subset of them. So this is 3 of your tetrahedra within the octuplex. These are another set of 3. The front, back one, left, right, front, back. And if you look at them all, it's this big kind of ugly mess. It's hard to make out much from it. And this is your unit cell. So you're actually going to have a honeycomb that's composed of a bunch of these attached to each other. And again, in a periodic lattice. Okay, so to summarize, what is the code? So you have this lattice, which is the octuplex honeycomb, which is given by this Schlafli symbol. And its vertices are 3-colored. The qubits live on octahedra, the 3 cells that are these 3, 4. The X stabilizers for giving code blocks for code block 1 are the red vertices. So the corresponding support will be all 3 cells that a given red vertex is in. The X stabilizer for the second code block will be blue vertices, for third code block will be green. And then the 0th code block, or this last code block, is special. And those are actually the 4 cells of the octuplex honeycomb itself. And again, the Z stabilizers are the intersection of the X stabilizers from 3 other code blocks. And you're going to get 1D string logical operators and 3-dimensional hyperplane X logical operators. Okay. And just to kind of emphasize how useful these Schlafli symbols can be, we can use them to derive the properties of the lattice, right? Because right now I've just told you what the lattice is. It's octuplex honeycomb, this object that mathematicians or geometers have shown that they exist. But you know, it's very hard, just given these numbers, how can I derive properties of the code? And this is like there's some really nice tricks you can play with Schlafli symbols. So a vertex operator is, if you look at it, given honeycomb, which is a general polytope, is if you look at the vertex and then for every adjacent edge, you place a vertex, and then for every adjacent face, you place an edge, and volume, you place a face, etc. So then this will represent kind of the adjacency of a given vertex. And so what it tells you is that for example, an example of the cubic honeycomb, every vertex has 6 neighboring edges and 12 neighboring faces, because that's the number of edges in the vertex operator, and 8 neighboring volumes, because it's the number of faces. And to calculate what the vertex operator, you can just look at the Schlafli symbol and chop off the first entry. So the vertex operator for the cubic honeycomb is just an octahedron. And then so you can read off all the properties you want by knowing the properties of the octahedron. In a similar way, you can kind of iterate this process and get the adjacency of an edge by taking the vertex operator of the vertex operator, so taking it twice. Okay. So if we wanted to calculate what is the weight of a given X stabilizer, so that corresponds to looking at the adjacency of a given vertex in our octuplex honeycomb. We just have to look at this vertex operator. And the vertex operator, again, is just chopping off the first entry. And that's going to give you this 433, which is a hypercube, which I told you before is a hypercube. And now as I said in the previous slide, the 3 cells in our original lattice become faces in the vertex operator. So then you just have to count the number of faces in the hypercube to know how many adjacent 3 cells there were in the original lattice. And that tells you that the X stabilizers here are weight 24, because there are 24 faces in the hypercube. And you can do a similar thing to calculate the weight of the special code, the other code block, and again, you'll get weight 24. Maybe I won't go into detail about that calculation here, as I'm running low on time. And you could also calculate the weight of the Z stabilizers. And this turns out to be calculating the adjacency of a face is equivalent to calculating the adjacency of a face. And so you could take this face operator, which is taking the vertex operator twice. So then if you chop off the first 2 entries, then you're going to get a 3, 3. And then you can just, by going through the process, determine that the Z stabilizers of this code are actually going to be weight 3 objects. So maybe I won't go into the details of this calculation. So you have weight 24 X stabilizers and weight 3 Z stabilizers. But of course, there's a great amount of redundancy in the Z stabilizers given in the form of meta checks, and that's because you could think of these. There's going to be a bunch of local redundancies because the Z stabilizers overlap multiple times, and kind of similarly to in the 3D toric code where you had locally a redundancy of the Z stabilizers, because for example, you take their product on a given cube, they cancel each other out. A similar procedure will happen here. And so this gives rise to the potential for single shot error correction in this lattice, because you have a local redundancy of all of these C checks. And you also have some global redundancies that are given by global properties of the lattice that are much fewer, but are important for counting degeneracies in the code that we refer to as global meta checks. And so this is important for consideration of decoding. Okay. And then you might ask, okay, can this generalize to higher dimensions? And it's not obvious, because the generalization of we are encoding our qubits on octahedra, and the generalization to 5D would be to go to hyperoctahedra, which is the 334. And so you might ask, okay, is there a lattice of this form, 334 AB? And there is no such lattice in 5D in Euclidean space, because the only such lattice is the hypercubic lattice in 5D. But there does exist such lattices in hyperbolic space in 5D. So, I mean, that could be of interest for different reasons, but it's kind of interesting that it doesn't naturally generalize. Okay, so maybe I'll just complete my talk there. So the idea here was we wanted to search for a code that had a transversal cccz gate, and to generalize the techniques that were introduced by Vasmer-Browne for overlap conditions between the X stabilizers of our code. And we found this octaplex honeycomb was a natural candidate, and we could calculate from the Schlafli symbols a lot of different properties of this code. And it's interesting that it's just not a straightforward generalization of the cubic honeycomb. And more generally speaking, it would be nice to know if these, can we get a better understanding of these overlap conditions so that we can understand transversal gates, you know, higher in the higher levels of the Clifford hierarchy for higher rate codes, not just codes that encode a constant number of qubits. So with that, I would like to thank you for your attention, and I would like to highlight again that if you have any questions, please feel free to send me an email, or to, of course, probably more useful for everyone if you just wrote it up on the Slack channel that we have for this conference. Thanks for your attention.
Okay, thank you, Thomas, for a very interesting talk. I would not have guessed that was the generalization of the 3D toric code that you need to get these control Z gates. Very unusual. So we've got one question by Andrew, which maybe we can come back to that one actually, because I think it'll be a longer technical answer. But anonymous attendee has also asked the question, what would be the practical application of this work? So I think you did touch on this earlier on in your talk, but maybe you want to recap on that.
Sure. I mean, I think really, to be frank, this is more of a high level theoretical interest. I did talk briefly about the implications. So here we end up having on this periodic lattice 4 logical qubits that allow you to do cccz gate transversely among the 4 code blocks, the 4 logical qubits. And so you could then use this to do a targeted CCZ on one code block. But of course, we're not going to go through this whole construction of building a 4D code just for that reason. But I think more generally, this could be applied to high rate codes. And I think that's where there's potential practical implementations. Now, in terms of, I think just building our understanding of higher dimensional codes has become useful for many areas of error correction at lower dimensions as well. So, you know, oftentimes our understanding of 3D codes help us intuitively improve on how to do fault tolerant gates, and also how to do decoding in 2D. So maybe a similar thing is, you know, increasing our understanding of 4D codes can help build our understanding of 3D and 2D codes. And you could do similar things of gauge fixing or dimensional jumps to go down to lower dimensions. So I think, you know, there could be practical applications along those lines, but yeah, it's not directly obvious.
Okay, thanks, Thomas. Okay, Mike Vasmer is asking, I think you hinted about this, but do the 4 codes actually have the same structure, even though the construction is different for the 4th one?
Yeah, that's a nice. I don't even realize. I didn't even realize if I did actually hint at this, but that's an astute observation. Yes, it turns out even though it wasn't by design, and we thought there'd be this asymmetry that 3 of the code blocks would be the same and 1 would be different. It turns out that in this lattice, the 4th one, you just find a relabeling of the 4 cells and the given certain vertices to actually show that they are equivalent and the 4 code blocks will be equivalent. And that's why I said they're all X stabilizers are weight 24 and Z stabilizers are weight 3. That's going to be true for all 4 code blocks, which is not true. Yeah, that was kind of an interesting observation. It's not true for the 3D code, right? There you do have to have this asymmetry, and I don't think there's any way around it, at least for a regular lattice.
Okay, Andrew Landell's got another question, but before he has his, I'm going to interrupt with my one, which was just you hinted at this Pauli sandwich trick, which I've also thought about in the past and not really found an application for. So you have to find like a high rate code to make it worthwhile doing, which has encodes a very large number of qubits and has a high distance and et cetera, et cetera. This construction that you gave, you didn't comment on the distance or the number of logical qubits. Was it just a single logical qubit encoded or a constant number?
Yeah, so it's just a constant.
Do you have a proof of the distance?
Yes, so it's a constant. It's only, if you have a periodic lattice, it's 4 logical qubits. If you decide to place boundaries, which I didn't touch on at all, then you get a single logical qubit. The distance is going to be, so your Z distance, which is your string-like distance, is going to be L. So if this is assuming you have a L to the 4, an L by L by L by L lattice, your Z distance is going to be L, while your X distance is going to be L cubed. Yeah, I think that's all. I think that answers that question. But yeah, I agree with you. I mean, this Pauli sandwich trick really becomes appealing for high rate codes. So I think that's really more of a motivation for we'd like to think about these overlap conditions in high rate codes. So, I mean, it's a hard problem. There's no obvious answer to where it could be applicable, but some motivation for all those attending this workshop to think about.
Okay, so maybe we'll close with one more question from Andrew before ending the session. So Andrew's asked, perhaps a quicker to answer question. Is the 5D hyperbolic code you mentioned a high rate code with good distance properties, like the ones that Nico Brockman and Vivian Longe recently discussed in archive reference 2001.3, sorry, 03568. Oh dear, just Google Brockman and Vivian Longe.
I'm pretty sure I know which paper you're referring to, and no, because yeah, this is not a high rate code. I guess, let's see, I touched briefly on this. For our criteria, where did I talk about this? I was talking about, yeah.
Hyperbolic codes are the ones that have high rates. And so the 5D one was hyperbolic. That's what I was asking about.
Yeah, it was hyperbolic. And so I don't remember exactly if their tessellation is exactly regular, or maybe there might be some slight irregularity. So I don't know if you can write it just in a straight Schlafli symbol like this. But yeah, so it's not the same code, but they also in their paper, they discussed the idea of using these Schlafli symbols to understand the regularity of codes and their usefulness. But yeah, they have high rate, but they're I don't think they discuss, Nico can correct me if I'm wrong, either here or in the Slack, I don't think they discuss logical gates there. And we're here, the idea of implementing a particular logical gate, that's very constraining. And so there's a lot of things you could loosen up, right? You could say, okay, well, what if it's slightly irregular? Because here I'm assuming every vertex, edge, face, behaves identically to all the other ones in terms of its adjacency and all this. And you can still have great codes that don't have exactly regular structure, and then maybe still find the logical gates we're after, maybe have higher rate. There's a whole spectrum of codes out there. But yeah.
Okay. Thanks, Thomas. And we'll thank all the speakers in this session.